Artificial intelligence, often known as AI, has transcended the realm of science fiction and has become an indispensable part of our human life. AI is now powering virtual assistants, it's driving autonomous cars, and it has truly permeated into every single aspect of our life. It has enhanced productivity levels further than levels beyond which you can even fathom. It has augmented human capabilities and revolutionized industries. I am here to talk about what AI is, how it is relevant in our lives, and more specifically on how a neural network is implemented to support AI to make predict. Okay.
I have heard about AI. In particular, I have watched The Terminator. So I do know that AI has a tendency to kill, does it? Well, be it science fiction, what else can it do actually?
That's a great question. And in fact, that's the first movie that I saw that talked about AI in a, well, mean manner. Let's just put it that way. And even I had the question. I was wondering on whether if AI would ever take over the world, if AI would form armies, if it would form hordes and start killing humans and start to establish authority. And I asked my trusted old friend, an AI, on whether that is true. And it's funny what it told me. It told me, yes, we are very strong, we are very powerful, but we are not that far away from going off. We are just one pull of the plug away from going off. Now, coming back to the topic of what else it can do, I bet all of us here are very lazy people. In fact, I can tell you that I am a very lazy person. And I'll tell you a brief experience that I had, let's say. One day I was sleeping, very peaceful, nothing happened, until it suddenly dawned on me that I had a presentation due for the next day and 2 assignments. What did I do? You guessed it. One tab, Gamma AI, one tab, ChatGPT. ChatGPT did both of my assignments and Gamma made my presentations, and my life was 10 times easier. I am here today to explain to you the brains behind these technologies, the brains behind AI, which is neural networks, and I am going to explain to you how it works. Neural networks, they are very similar to our brains. In fact, they are so similar, and that's why they got their names as neural networks. Each component of a neural network is called an artificial neuron. Now, let us take a step back. Let us take a step back and see how our brains process things. When you were a baby and you start taking in all of the things that occur in the world and your brain develops certain connections between them, when you do math, your brain starts processing things and it makes tiny connections. Okay, this isn't the right way to do something. Correct in our brain, and our brain forms these tiny connections. Neural networks are basically how the computer does these things. It has artificial neurons and it has connections between them, and how a neural network improves is by feeding it new inputs, and when a new thing comes, it generates an output and then we correct it based on that. So it goes back to the connection just like a human brain does, just like a child does, and it thinks again and it corrects it. And that's how they give new outputs.
But Deva, you see the brain is actually a biological thing, right? What exactly is the structure for this neuron that you just mentioned?
That's a great question. Now, if we look at the human brain, we can see that it's a very complex mechanism that goes on in there. And when we compare it to the neural networks, as you said, it's very simple. Neural networks are very simple when we look at it and compare it to an actual human brain. Because a neural network has mainly 3 components: an activation function, a bias, and a loss function. Now, an activation function is what determines the output of a neural network. The bias is the assumptions that it makes to get to that output, and the loss function or the error is basically the errors that a neural network makes, and we use this to correct the output of the neural network. Now, first we are going to talk about what a bias is. Now, we all have those girls in our class who start studying 3 days before the exam, in fact the maths exam, and they start memorizing every single problem. They open a text, they see a difficult problem, okay, this is very likely to come for the exam, and I can't figure out how it works. Might as well by heart the entire thing. They by heart one problem, fine. They see the next problem. They still haven't developed the connection to what's happening, so they by heart that as well. Fine. They see the next thing, they do the same thing. And this goes on for every single problem in the textbook. What is the issue with this? They sit in the test, when they get a question, they don't know to answer that. They don't know how to connect these concepts together because they know how to solve x square plus 2. They don't know how to solve x square minus 2 because they don't know what it does. Now, let's just say another student in the same class did only 2 of those problems. But in the process, he has learned how it works, how each of the steps works, how it contributes to the output, how it contributes to the solution. Now imagine you throw a new question at him in the exam. He's going to do that very, very simply. This is what a bias does. A bias is the assumptions that are made when a neural network predicts its outputs. And just like the girl, if you make very little assumptions and you by heart everything, you're essentially training yourself to only write what you learnt about. You know your name, you'll write about it. They ask you something else, you don't know what to write about. But let's just say the other person. Let's look at the other person who studied everything, who studied the concepts. Now, if you ask him a different question, he's going to be able to generalize so very well. And these are the concepts of overfitting and underfitting. A model that has very little bias will not be able to generalize the outputs, will not be able to predict new inputs well. Whereas a model with some amount of bias, with some amount of ability to make new assumptions will be very, very good at giving the right outputs. And that's what a bias is. The next thing is our activation function. And for this, we have all driven cars. Most of us have driven bikes too. Now let us move on to the second and another important part of a neural network. That's the activation function. Now, what is an activation function? An activation function is that complex equation that determines whether the neural network inputs yes, no, or any other output at the end of it. Activation functions are often present at the output layers, and these determine the output of the entire neural network. Then we have errors. We all know we make mistakes, and sometimes our neural network and the activation functions can also make mistakes. Errors and loss functions are what determine the degree of mistake our neural network has made. If our neural networks deviated a lot from the actual output, then we say the error or loss function is high. If it deviated a little, we say there is a little error, or the loss function is very small. Now let us work out a tiny example with these 3 concepts. Now, this is the structure of a neural network boiled down to its simplest form, having each of the components I mentioned just earlier. For this, I am going to use one of my most favorite examples that all of my friends love to hear when I talk about neural networks. Imagine that a girl is being approached by a guy. Now, let's just say that the girl likes a guy who can sing very well. So, that can be one input. Sings very well. The girl loves a guy who can sing very well. Now, the girl maybe isn't that into a guy who can dance. So, the second characteristic for her saying yes would be whether he dances or not. And the third thing, which I don't know if it's good or bad, but the girl is into people who don't study that well. She likes people who are a bit adventurous, don't get into class, the troublemakers, let's say. And let's just put that as our third output. It's a studious person. Now, each of these inputs contribute a certain amount toward the girl's decision is. And these amounts that contributes are basically the weights. Each of these inputs have a certain weight on the output of the neural network. Let's just say the girl cares very deeply if a guy sings or not. So the first weight, or the weight of whether a guy sings or not, can be 0.3, let's just say that. And she doesn't care if the guy dances. So the weight can be 0.01, and again, she loves the troublemakers. That means the guys shouldn't be that studious. So let's just say that the studious people loses some of her points. So the weight for that can be minus 0.5. That means if a guy is very studious, she actually loses interest. Yes? No. Imagine that she's being approached by a guy. Now let's just assume that the girl needs at least a 5 for her to say yes. So we are going to put that. That's going to be our activation function. That the marks that a guy gets on her scale should be at least 5 for her to say yes. Now, let's see how a 5 is calculated. Let's put our weights down. Singing had a 0.3, dancing had a 0.01, and if he studies very well, oh, he's done for. He gets a negative 0.5. Let's say one guy approached her, and this guy 1, he sings amazing. He sings very, very, very well. And he has 10 marks on singing, and this singing is going to contribute to the final output as his marks on singing times the weight singing has in her scale. Then we'll add his dancing skills into this. He dances terribly. He gets a 0, which again is multiplied by the weight. And let's just say that he studies very well. He has a 5 on the studious scale, and that's actually going to cost him some points on the scale. What does this amount to? This 0 is going to get cancelled. 3 plus minus 2.5. That means she said, you guessed it, no. Guy 1 got rejected, sadly. Now let's look at guy 2. This guy, he doesn't sing that well, but it's bearable. And let's just say he gets a 7 on the singing scale. 7 is going to amount times 0.3, and he dances very, very, very well, and that's going to get a 9 times 0.01, and he is the biggest troublemaker ever. That means he doesn't even study, and he gets a negative, let's say, negative 7 on the study scale. That's going to amount times minus 0. What does this amount to? This amounts to 2.1 plus 0.09 plus 3.5. And I don't know what this number is, but it is greater than 5. That means she said yes to this guy. Yes.
Finally, you might be wondering, I explained about weights, I explained about inputs and what the output is. We left one thing in between. We left the bias term. When we think about it, bias is the assumptions that we make. Or in very, very simple, very basic terms, it can be whatever we give to something that is going to shift the output in a certain way. Let's say that if the guy owns a Duke, this girl loves to go on long bike rides at night, and let's just say if this guy owns a Duke, then that's an instant plus 10 for this girl. That means if our first guy really, really wanted to get this girl, he goes out of his way, he gets a Duke just to impress this girl, then he'll get an additional 10 on the score, and that has shifted his output from a no to a yes. That means if this guy or if any guy has a Duke, that instantly adds bias to the output of our neural network, and this is what a bias actually is. It shifts the output from a certain value to another value for every input.
You mentioned these 3 characters. The second guy clearly seems to be a bad boy, and the activation function says that yes, he will get accepted by the girl. But what if the girl actually says no? Well, there's always a room for error, right?
Great question again. Now, this is very, very probable in a neural network. In fact, in our lives, for this girl, this can be very possible because we are making this output. We are taking this prediction based on the values of certain inputs and certain outputs which are calculated with certain weights. Any of these can be erroneous, any of these can be wrong or slightly deviant from the actual value, and this is actually going to cause errors. Yes? How we fix these errors is basically by using the loss function. So now, let's just think of it as this way. Our girl was asked out by a guy who clearly had a probability of yes from our own equations, but he got a no. We are not going to say that the girl was wrong because the girl is clearly the one to make the decisions. We know that our equations are wrong. Somewhere in our calculations we went wrong. So we take this error, we take this wrong output and we put it into our loss function, and then we find out how much of this error is caused by what all weights, what all values that we put into our function. Now, I'll give you guys a very, very interesting example of how we deal with errors. Let's say our model has very high error. You are at the top of a mountain. How do you get to the land beneath it? How do you climb downhill? Do you jump from the top? Do you want to die? Or do you want to take the long route by going all the way around the mountain? Or are you going to take small steps one by one, tread downhill, down the right path and get to the bottom of the mountain? Yes, any sane person would guess the third option. They would want to take slow, tiny steps and get to the bottom of the mountain eventually. This is in fact called as gradient descent in machine learning. Let me visualize it for you guys. Our model predicted yes, but the girl said no. And that means our model is wrong somewhere. The weights that were used to calculate the output went wrong somewhere, and we are going to have to readjust these weights if we want a better accuracy, if we want a better prediction and the right prediction. Now, this is done using gradient descent. I'll visualize it for you guys. Imagine we have a very high error for a particular value of a certain weight. Let's say theta 1. Now, to get downhill, to get to the most optimal value of theta, it's going to have the least error, and that's going to be here. Now this is going to be theta O. It means that's the optimal value of error. Yes? Now how do we get from up here, from the top of the hill to the bottom of the hill? We take the most optimal path. Now, this optimal path is decided by a value known as alpha. Let's write alpha down here. Alpha is called the learning rate. This value is of very much importance to us. It's of very, very high importance because this value alone is going to decide how fast you reach the optimal solution and whether or not you are even going to reach it or not. Yes? Now, the equation is going to go somewhat like this. If you simplify it, theta I plus 1 will be equal to theta I minus alpha times partial derivative of error caused by theta 1. I know at one glance is a lot to take in, but let's break this equation down. How do we modify something? We modify it by making certain changes to it. Now, what is partial derivative of error by partial derivative of theta 1? We all know about partial derivatives. Partial derivatives are used to find the changes to something caused by a particular value, in that function, and that is exactly what we are doing here. We are trying to find the amount of error that's contributed by theta 1. Yes? And now that we have the amount of error contributed by theta 1, we have alpha, which we said that it was the learning rate. This is going to determine how much this error is going to affect the new value of theta 1. If alpha is very large,
then we are going to affect the new value by a huge margin. And this is going to abruptly change the value of this parameter, and we are not going to convert it to solution. Optimally, we take alpha to be somewhat in the range of 0.01 or very small values, so that our model can take tiny steps to tread downhill and downhill until it reaches the solution. Yes? And it's very simple actually. For every iteration, you find the new value of the parameter, you update it, you find the error again, and then you find out how much of this error is contributed by your new value, and then you put it again into this equation. It's an iterative process, like getting downhill. You take the first step, okay, you look at where do we have to go again. You take the next step, and you take the next step, and finally you reach the bottom of the hill, and you reach the most optimum output of the neural network. And that brings us to the last topic of this session, which is accuracy. Now imagine we put our model out into the market and 10 guys use this. Out of these 10 guys, let's assume only 2 guys got their correct output, and the rest 8 of those guys, either they were told that they would get a no when in fact they should have gotten the girl, or this is the worst part, or they were told that they would get a yes when the girl was going to embarrass them. Now imagine the second group of people. The model gives them extra fake confidence. The model is like, you are going to get the girl. And when they go and ask this girl out, this girl is going to be like, who is this dude? And that one thing is going to taint their self-esteem for the rest of their life. And if it was my model, I wouldn't want it doing that kind of a thing to people. And this is why we need a high accuracy for any model. Now, several factors determine the accuracy of a model. One of it is going to be the error rate. Now, the error rate, it can be minimized by certain methods like gradient descent or any other error reducing method. But then there are other factors like the quality of the training dataset, the amount of features that we use, etc. I'll give you an example. If our dataset is only going to have one type of attribute, let's say only going to have 100 guys who got yes, the model is never going to be able to tell when a guy is going to get a no. And these are only certain things that would determine the accuracy of the model. Now, with all of this being said, a good model will have an accuracy of at least above 90%, but the threshold is around 95 to 100%, and that would mean that our model is very, very good. This brings us to the end of our first session. I encourage you guys to go out and explore more in this field, because what is coming forward, what's going to happen is AI. AI is what's going to be the booming topic when you're in your 20s, when you're in your 30s, when you're looking for jobs, and being very well read in this topic is going to determine the chances of you getting a great job. There are many resources out there, and any one of you who has sparked an interest by this session can go out there and learn much, much more and delve deep into the world of AI. I assure you guys that there are going to be even more interesting, better sessions that are going to be taken by my friends throughout these coming days, and I encourage you guys to come back and listen to all of those. Thank you.